Hi everyone, this video is created for education purpose only. Myself, Meena Alable. I am head and assistant professor in the Department of Mathematics, Rayat Shikshan Sanstha, Maharaja Jivajirao Shinde Mahavidyalaya, Srigonda District, Ahmednagar. Dear students, we are studying our first year BSc, semester 1, Mathematics, paper 1, Algebra, and we have already started our unit number 1, Sets, Relations and Function. In the previous lecture, we have covered the concept of sets and relation. In this lecture, we are going to see what is meant by functions, and further we'll see types of function. So first of all, let us see what is meant by a function. So let capital A and capital B be non-empty sets. A function, it is also called as a map or mapping, and it is denoted by small f. A function f from set A to set B is a rule that assigns to each element in set a unique element in set B. This is important. F is a rule that assigns to each element in a unique element in B, and it is denoted by F. This colon is there, and capital A to capital B, and we read this as F is a function from set A to set B. You can represent function graphically in several ways. Like you can represent function by using Venn diagram like this. You can represent function by using graph also. And this is the graph, and this is the plot of function. In the end of this unit, we are going to see graphs of some standard function. Let us see some function terminologies. For that, if f is a function from set A to set B and f of small a is equal to B, where this small a is the member of set capital A and small b is the member of set capital B, then this RHS set capital A is called domain of the function f, this capital A, and this RHS set capital B is called codomain of function f. And if you have f of A equal to f of B, then this small b is called image of A under f, and conversely this A is called pre-image of B under f. And the collection of all images of elements in set capital A is the range of function f. Obviously, where images goes, so in the set capital B, and therefore your range of given function, it is sometimes denoted by capital R, and it is contained in B and is the set of all small b in capital B such that f of A equal to B, means B is image of some element in A. Then this set is called range of given function f. So let us see how to find range of given function. So consider an example. Suppose that f is a function which maps student in this class to the set of grades, and grades are capital A, B, C, D, E. So first of all, what is the domain? On which set you are defining this function? So set of all students in this class. So this is your domain. And what is the codomain? So students maps to where? It's their grades. So we have given the set of grades, and this set is nothing but your codomain. And what is its range? We don't know the range of this function, means we don't know which student have got which grade. And suppose that grade turn out all A's and B's, means all all students in this class have obtained either grade A or grade B, means no students in this class have got grade C, D, E. Only grade A and grade B are there, and therefore the range of given function is set capital A and capital B. These are the grades, and why these grades? Because every students got either grade A or grade B, and therefore this is your range of given function, where still its domain is the collection of all grades A, B, C, D, E. So remember, for this function, domain is the set of all students and range is the collection of grades capital A and capital B. Let us see some more examples. Find domain and range of the function f of x equal to e raised to x. So this is your exponential function. We have to find domain, means we have to find x for which this function f is defined, means we have to find the values of x for which this e raised to x exists. But if you put x equal to 0, what is e raised to 0? It is 1. If you put x equal to say 2, so e raised to 2 is whatever, doesn't matter, it is positive. And if you put x equal to minus 2, so what is e raised to minus 2? So e raised to minus 2, if you take reciprocal of this, so you will get it is 1 upon e raised to 2. So it is defined. Now obviously that belongs to, where it goes, that belongs to set of real number r. So it is some real number, doesn't matter. If you want, you can put e equal to 2.71, make it squares and take its reciprocal. So we know that e raised to x is defined at every real number x, and therefore domain of f of x is the set of real numbers. Means to find domain, you have to identify for which value of x f of x is defined. In this case, for every real number e raised to x exists, and therefore set of real number is the domain of given function. Now let us see how to find range of the given function. So range of the given function means we have to see where this e raised to x goes, means whether e raised to x is 0, positive and negative. So e raised to x is never 0, so this is not allowed. E raised to x is always positive, so e raised to x is never negative, so e raised to x is always positive. So e raised to x is strictly greater than 0 for every x belongs to R, and therefore your range of the function is set of positive integers R plus. Here R plus denotes set of positive real numbers, and if you want, you can denote it by using interval also, open interval 0 to infinity. Why open interval? 0 is not included because you cannot find x for which e raised to x is 0. So it is simply a positive real numbers, and therefore we have a function from here to here, r to r plus, where this r is your domain, first r, and the second r plus is your range of the given function f of x equal to e raised to x. Similarly, see the second example. Find range and domain of the function f of x equal to log x. So to find the domain means you have to find x for which this function exists, means you have to find x for which logarithm x is exist. So we know that for x equal to 0 and x negative, you cannot define logarithm. So log x exists for only positive real numbers. So domain D is R plus set of positive real numbers, and we have to look where this logarithm goes, whether this is positive, negative, or 0. So log 0, log 1 is, you cannot define log 0, so log 1 is 0. So it is, if you take a number less than 1, then you will get logarithm is negative, and if you take number greater than 1, your logarithm is positive, means logarithm is 0, negative, positive, and therefore its range is a complete set R, set of real numbers. So we have a function f from R plus to R. So R plus is your domain, and this R is range of the function f of x equal to log x. So this is how to find domain and range of the given function. Let us see one more example. Find domain and range of the function f of x equal to sin x, trigonometric function. So to find domain, we have to find x for which sin x is defined. But we know that sin x exists for every real number x. Therefore, domain of the function is set of real number R. To find range, we have to identify where this sin x goes, but we know that, what is that? Sin x lies between -1 and +1, so -1 less equal sin x less equal 1, and therefore your range means sin x lies between -1 and +1, and therefore your range of the function is closed interval -1 to 1. So this set of real number R is the domain, and closed interval -1 to 1 is the range of your function f of x equal to sin x. You can find domain and range of some other function like cos x, tan x, etc. Let us see another terminology, function composition. So for that, consider three sets, capital A, capital B, capital C, and suppose small f and g be the functions such that f is a function from set capital A to set capital B, and g is a function from set capital B to capital C, and in that case the composition function of f and g is denoted by g composite f, and see, this is not 0, so this is g. You have to read this as g composite f, and it is defined as g composite f. You will get it is a function from set A to set capital C, and how to take the image of elements in A. So g composite f operating on A, so it is equal to g operating on f of A for each small a in capital A. So this is the definition of composition. So remember, as your f of A belongs to B and g is defined on the set capital B, so your g of f of A is defined, and where it goes? So it goes in capital C. So it is in C. So to define the composite function g composite f, condition is that range of f must be the subset of g. So here range of f is contained in B, and the domain for G is B, and therefore you can say that range of f is contained in the domain of G. So remember this result, range of f must be the subset of G's domain, and this is first composition map G composite F. You can define F composite G. So to define F composite G, what you have? You must have the range of here. To define G composite F, your range of this G must be the subset of domain. Range of this F must be the subset of domain of G, and to define F composite G, so you must have range of this G is contained in, or it is a subset of domain of F, and therefore you can say that these two composition maps are not equal. So F composite G is not equal to G composite F. So let us see how to find composition. So for that, consider a function f from R to close open 0 infinity. So f is a function from R to close open 0 infinity, and the function is f of x equal to x square, and one more function is given g from close open 0 to infinity to R. It is defined as g of x equal to root x. Find f composite g, g composite f, and further we have to identify whether these two composition maps are equal or not. And here uh, range of f is contained in domain of G. So range of f is contained in domain of G, and therefore G composite f is defined. Again, range of G R is contained in domain of f, and therefore you can define f composite G also. So here range of f, I have mentioned here, range of f is contained in the domain of G, and therefore G composite F is defined, and we have seen the definition of G composite F. So G composite F will be the function from where to where? R to R, and it is defined as G composite F operating on X is G outside, then F operating on X. So G as it is, what is f of x? We have given f of x equal to x square. So G operating on x square. So what is G? G is square root. So you have to take, so apply G on this new variable, say alpha. So what is G of alpha? It is square root of alpha. So square root of x square, and in real number, so you have to take a positive square root, so mod x is there. So G composite F is mod x. Now another composition map. So for that, range of G is contained in domain of F, and therefore F composite G is defined. And what is its definition? So you will get F composite G from where to where? Close open 0 to infinity to close open 0 infinity, and this F composite G operating on X is F outside G operating on X, and whatever this element is there, then you have to apply F on that. So what is G of X? So it is square root of X. Now this is new variable, say beta. Apply f on beta. So what is f of x? It is x square. So what is f of beta? Beta square. So where whatever this number is there, so you square of that variable. So square root of x and is square. So square root will get cancelled, and it is simply x. So f composite G is x, and G composite f is mod x. And obviously these two are different, and therefore you can conclude that f composite G is not equal to G composite f. So remember how to find F composite G and G composite F. So for that, this condition is very important. Range of F is contained in G, then you can define G composite F. And if range of G is contained in domain of F, in that case you can define F composite G. So I am giving you one exercise to find composition mapping. So let F and G both are functions from R to R, and the definition as f of x equal to x cube plus 3, and the definition of g of x is cube root of x, and find f composite G as well as G composite F. Now here Both composition maps are defined because domain and codomain of F and G are same. Also, you can identify whether two composition maps are equal or not. So, remember this and let us summarize what we have seen in this lecture. So, we have seen the definition of function, then we have seen how to find domain and range of the given function, and in the last we have seen composition of given two function, and we have seen the examples how to find composition of given functions. This is all about functions. In the next lecture we'll see types of function, means what is meant by one function, what is meant by onto function. Let us stop here.